Hello everybody once again. If you'll go ahead and if you have your notebook, you can put this in your table of contents, new title, gears, pulley drives, and sprockets. Put this on top of the page, box it in, today's date next to it. If not, you can put it on another piece of paper and then attach it in your notebook when you get back to class and have your notebook in front of you. We're going to look at some new machines that deal with simple machines that kind of add to our knowledge about mechanisms and devices. So here we go. Gears, pulleys, and sprockets. The three powertrain elements transfer energy through rotary motion. Write this down, please. The three changes. So they change the speed of rotation, change the direction of rotation, and change the amount of torque available to do work. In this first picture here on the left, you see the front of a car engine, or the front cover, timing cover, has been pulled off, and you see these gears that are meshing. That helps to do with the timing of the engine, the firing of spark plugs, and moving of pistons and valves and lifters, things like that. The middle picture here is actually just a riding lawnmower. What we're looking at here is actually the underbelly of the lawnmower, but the top of the deck of the mower. So you see the pulley going around, belt going around the pulley right here to make the blades underneath that spin. That's how it transfers the motion. And in the far right picture, you see a motorcycle, of course, with a big giant sprocket on the wheel, and then a chain going around that, and that's how it transfers the power from the transmission to the wheel. Gears, talk about those first. Gear train is a mechanism used for transmitting rotary motion and torque through interlocking teeth. Gear train is made when two or more gears are meshed. Drive gear causes motion, and the motion is transferred to the driven gear. I'll definitely write down the last two lines there about the driver gear and driven gear. That's very important to know which one is the output and which one is the input. Of course, your driver is the input, and then your driven is the output. So to make sure you keep those straight as you try to solve for gear ratios. And gear ratio is kind of another word for mechanical advantage. How is it going to make my life easier, basically? You can think of it like that. Maiden gears always turn opposite directions. An idler gear allows the driver-driven gears to hit in the same direction. And maiden gears always have the same size teeth and diametric pitch. You'll write all that down in your notebook. It's very important to remember. If you've seen the animation, it's explaining how the left blue gear is turning in a clockwise motion, where the right gear, the red gear, is turning in a counterclockwise motion. So therefore they turn in opposite directions. But in the lower animation, where they've added an idler gear here, that allows the two blue gears to turn in the same direction. It's important to note here also that idler gears do not affect your gear ratio, at least in a simple gear train. So an idler gear does not affect your gear ratio in a simple gear train, which we're looking at right here, right now, is a simple gear train. These are just all gears lined up that are all meshed together. Idler gears are just there to change direction, or in this instance, maybe even take up space. Maybe they had space to fill between these two gears, and they also want to make the two blue and turn in the same direction. So an idler gear comes into play there, but it does not affect the overall gear ratio. RPM of the larger gear is always slower than the RPM of the smaller gear. You can write that down if you'd like to, but it's kind of self-explanatory. So obviously if it's larger, it's going to spin slower than a smaller gear. You can see that with the green gear, large green gear compared to the little smaller red gear. Gears locked together on the same shaft will always turn in the same direction at the same RPM. You can write that down also if you'd like to. It's also self-explanatory. Obviously if they're tied to the same shaft, one gear cannot spin faster than the other. If you want to write down these variables, what the symbols mean, you can in your notebook. We're going to see the actual equations here in a minute, but N is just number of teeth. D is diameter. That's the overall diameter of the gear from outside of the teeth. This is using W as the angular velocity or speed, and that would be given in RPMs, revolution per minute. And of course you have T as in torque, and that is the torque that's either input or output here. So in these two gears, we have a red gear, as they're calling the N on the right side, has six teeth, has a diameter of 2 inches, a RPM of 40 RPMs, and a torque of 40 foot-pounds. The marking the blue gear, the out, in out, so 12 teeth on that gear, 4-inch diameter, 20 RPMs, and it is 80 foot-pounds of torque. So then if we look at our gear ratio equations, you'll need to write these down. Notice the symbols have changed a little bit. The symbol for speed, there was a W a minute ago, this actually is the Greek letter omega. So you'll tend to see that more often. And then the T is no longer a T anymore. For torque, this is actually the Greek letter tau. So you have torque out over torque in, omega in over omega out. You have diameter out over diameter in, and the number of teeth out over number of teeth in. So the N and D did not change, but the omega and the tau did change from what we saw in the previous slide. So sometimes you'll see W's or omega, sometimes you'll see T's or taus. It just depends on what kind of font the people are using to either write the textbook or to write the test. So what I do want to point out here is, you notice out of all these equations or parts of it, omega is one that stands out. So I would mark that somehow, box it, circle it, put a star by it, because all of the other equations are all out over n. Omega, or angular speed, is the exact opposite. It is n over out. So I don't need to get that confused and get that one wrong. So we look at our examples here of the red and blue gear. We put all these in. Our gear ratio we don't know yet, but we can solve it pretty simply. The number of teeth out over number of teeth in is 12 over 6. Diameter is 4 over 2. Omega, our speed, would be 40 over 20. It's in over out. And then our torque is going to be 80 over 40. And so they all simplify a ratio of 2 to 1. So that is our gear ratio. This, once again, is a simple gear train. So they're all just lined up, all meshed together. So what is the gear ratio between gears A and gear B? We'll notice A here is the first one on the left. We'll take that as our input. And then in this example, just with these two, B would then be an output. Not our final output of the system, but an output. So we would divide those gear ratios. Or find the gear ratio, we divide number of teeth out, number of teeth in. So it would be 12 over 20. So it would be 0.6 to 1. And then for the gear ratio between B and C, now for this example, between B and C, B would be our in and C would be our out in this example, in this part of the problem. So we would then divide our 5 over 12. So we get 0.42 to 1. And then for the last ratio, finally, we have between C and D. So then D is out and C is in. So that would be 20 over 5. And that gives us a ratio of 4 to 1. Like we saw in the last presentation, when you want to find a compound mechanical advantage, or here a compound gear ratio, we would just simply multiply all of our gear ratios. So 0.6, 0.4, 2, and also 4. When we do that, multiply all those together, we get a ratio of 1 to 1. So we really don't have any advantage here. Well, if you look, remember I said earlier, either gears, that would be B and C, do not change gear ratio. They only affect the direction the gears turn, and then maybe would take up space. So if you were to look at directly between the two gears that are really affected, A and D, right, A being your input and then D being your overall output, we could simply divide those two and find the gear ratio much, much quicker. So this time, if we look at A and D only, A being in, D being out, we would do 20 over 20, and we get the exact same gear ratio of 1 to 1 to show you that either gears in a simple gear train do not affect the gear ratio. If the last gear had 40 teeth, what would be total gear ratio? Well, if the last gear had 40 teeth, we could redo the math, or we could do it much simpler and ignore the idler gears, and we would just simply do 40 over 20, and that would be 2 to 1. So if D instead had 40, we would divide 40 over 20 and have a 2 to 1 ratio. Or you could do it the long way over here in the black font and use idlers, but we know that's just wasting time. Gear ratio in compound machines are used similarly to mechanical advantage, apply to torque instead of force. So here you have force out, mechanical advantage times force in. You have torque out is gear ratio times torque in. In a compound machine, total mechanical advantage gear ratio are products and components, like we saw earlier, time the total mechanical advantage, it's MA1 times MA2 times MA3, etc. Gear ratio total, gear ratio 1 times gear ratio 2 times gear ratio 3, etc. Mechanical advantage is used only to calculate forces, not torques, and gear ratio is only to calculate torques, not forces. While all this is true, we still treat mechanical advantage and gear ratio the same, because whatever it is we're doing, they're still giving us an advantage, right? We're either reducing our effort force or reducing our effort distance, so they're therefore still an advantage. So we treat mechanical advantage and gear ratio as an advantage overall. So here's an example of a compound machine. They have a wheel and axle. So we see this handle at the outside of it. That'd be wheel and axle from center to the outside. Then you have a gear ratio between the pink and the blue gear. And then you have another wheel and axle out here, once again from the center to the outside of the handle. So to find this, we would find the mechanical advantage of the first wheel and axle. Our effort distance would be the length of the handle. That would be 4 inches. And then our resistance distance, or DR, would be 1.5. And all that is the radius of the first gear. So they give us 1.5 inches. So from the center to the outside of the gear, 1.5. We divide that, 4 over 1.5 inches cancel, we get 2.67. For the gear ratio, we look at the number of teeth out over in. So therefore, we have 24 teeth and 60 teeth. So for this one, the blue gear, the smaller ones are output, so we would divide 24 over 60, and that comes out to a gear ratio of 0.4. And the last wheel and axle, mechanical advantage there, we see 4 inches from the center to the outside of the handle, and then that gear has a small radius of only 0.6 inches. So we see 0.6 inches divided by 4, inches cancel, we have 0.15 is the mechanical advantage of that last wheel and axle. Here they're only going to worry about the two mechanical advantages of the wheel and axles, so 2.67 and 0.15 gives you total mechanical advantage of 0.4, and they treat the gear ratio separately here, and they leave that as 0.4. Later on, when we build a compound machine and 1.1.6, we will actually multiply all of our advantages together to see what our overall advantage is of our entire system. But they don't do that here right now. Now we get into compound gear trains. So there's a little twist here. So they're going to build this thing together for us. So here's our driver. And those two mesh, the green and the yellow. And then we have our blue. So now blue and yellow share a shaft. So they will turn at the same speed. And then finally we have the red and blue meshing to give us that ratio right there. So this is a compound gear train because the blue and yellow share a shaft. And we only see two meshing here. The mesh between the green and the yellow, and then between the blue and the red. So the middle two gears share the common axle, so they rotate at the same speed as we discussed earlier. This allows the final gear to rotate slower and produce more torque than if we're connected only to the driver gear. We need to find the gear ratio between A and B first, since they do mesh. So we see 40 teeth at B and only 10 teeth at A. So they'd be out over N. So we have 40 over 10, or 4 to 1. For the other mesh, it'd be 50 teeth and 20 teeth, D being the out, and then 20 being the in. So 50 over 20, we get 2.5 to 1. So the entire gear ratio, we would have to multiply, since this is compound. We multiply the 4 to 1 times the 2.5 to 1, and we get a 10 to 1 ratio. So that is the advantage of this system. For belt and pulley systems, we write these equations down. We see the diameter out over N again. We see the omega, or angular speed, in over out. Remember that one is opposite. And then torque, we see torque out over torque in. And they give us an example here of these red and blue. So if we plug those numbers in, we have 6 inches out over here on this blue pulley, and then 2 inches in. For the angular speed, we have 30 RPMs is our in, over 10 RPMs out. And then our torque, we have 15 foot-pounds over 18 1/3 foot-pounds. Either way, they all simplify to a 3 to 1 ratio. And then last but not least, we have chain and sprockets, and we have the exact same equations. You want to write those down. Just remember angular speed is the opposite. And for the example, we have 22 over 11, 3 over 1.5, 90 over 45, 120 over 60. All the units cancel. Either way, it still comes out to a 2 to 1 ratio for this system here. And the different methods, you have pulleys, you have belts, quiet, no lubrication needed, expensive, can slip, however. Chain sprocket, you have a chain, no slip, greater strength, but there's a higher cost in these lubrication, and they can become noisy. That is it. You can cross the page out, sign the lines, my page witness sign date. If you have witness there, if not, find one in class. If you have any questions, let me know. We'll work on this in class for this assignment, but right now all you need for this part is your notes. Thank you and have a good day.